G'day everybody. In our video today we're going to look at solving logarithmic equations. In particular we're going to pay attention to how do the log laws enable us to solve logarithmic equations, and finally when is it important to consider whether or not the apparent solutions of an equation actually exist. Let's just do a quick review of the log laws. So the log of 1 for any base is equal to 0. When we've got the log of a to the base a, when those two things are the same, that simplifies to 1. When we can express m to the power of p in our logarithm, we can make p the coefficient of that expression. We have the addition laws or the subtraction laws, so when we add two logarithms together, provided that they're the same base, I can multiply m and n. When we subtract, we're going to divide m by n, and occasionally we might find a need to use the law that enables us to change the base of a logarithm. So in this video today, you might pause the video just to attempt the problem on your own first. I think it's a good idea. We're only going to look at 3 questions today. So first up, just a very simple logarithmic equation. Solve the log of x equals 4 when the base is equal to 3. So pause the video and come back when you're ready to look at the solution. So quickly, let's break this down. You can see here that I'd like to introduce a logarithm on both sides of the equation. This is going to enable me to get x by itself later on. So we're taking advantage of the fact that we can multiply 4 by 1, where 1 is in the form of a logarithm. The log of 3 to the base 3, carefully choosing the same base as the one that's on the left-hand side of the equation. We can take the 4 and I can write the expression like this. We've got the logarithm of 3 to the power of 4. Now we can see that we've got the log of x is equal to the log of 3 to the power of 4. This means that x must actually be equal to 3 to the power of 4, which is equal to 81. So the solution of our equation is 81. Just making those log laws explicit, you can see here where we've used the second law, the log of a to the base a is equal to 1, choosing 3 as the value of a. And in going from this line to this line, we've used this law where we move the value p from the power m to the power of p to the coefficient of the expression. Here's our second equation for today. Not a terribly complex one, and I'm going to let you pause the video, give you time to solve that on your own. So this really is very similar to the first question. We've introduced 1 again. Here the base of the logarithm is Euler's number e, so I've got the log of e to the base e. In the same way as before, we can see that the 2 is shifted in that expression. We've got the log of e squared. This gives us a logarithm on both sides where the base is the same. So from here we can deduce that x minus 2 must be equal to e squared. Adding 2 to both sides of the equation, the solution for this equation is e squared plus 2. So here's a solution where, because of Euler's number, we have no other way of simplifying this expression, so that's the exact way to write the solution. Of course, we can find an approximate solution using the calculator. And again, same logarithms as I used in the first equation. We're using that second law there, where we're really using 1 in a tricky sort of way, choosing the right base for this equation. And again, this is one we'll use quite a lot when we work with logarithms, being able to work with the value p there, moving it from the coefficient to the power. The final equation that we're going to look at today is the more complex one. Have a look at the log laws if you're not sure what to do first off, but I'm going to give you a moment if you'd like to pause the video now, attempt the equation, see how far you get. Okay, here's my solution to the equation. You can see here we've got an addition of logarithms, sorry. So we're adding those two logarithms together. Importantly, that's the same base. So I've multiplied x minus 2 by x plus 3. We already have a logarithm on the right hand side of the equation. So now we've got two logarithms that are equal to each other. We can deduce that x minus 2 times x plus 3 is equal to 14. So at this point, we're looking at a quadratic equation, and we deal with that the same way as we've always dealt with quadratic equations. You've got options. We can use the null factor law. We might complete the square, get x by itself. We might use the quadratic formula. In this case, I have expanded those factors, group terms, made the right-hand side equal to 0, factorised again, and the solutions of the quadratic equation are -5 or +4. Let's have a look at the logarithm laws that we used there. We have used the same base law where we're adding those two expressions together. That's enabled us to get one logarithm on the left-hand side of the equation. At this point, I want to ask the question, do my solutions seem reasonable? And this is I guess it's a tricky thing about these types of equations. We've got two apparent solutions for x, which seems reasonable when we've got a quadratic equation. But our original equation wasn't from a quadratic function, so we've got logarithms up here. And I need to think about whether -5 and +4 are suitable for this equation. One thing that we have to remember is that whatever we're finding the logarithm of, that quantity needs to be a positive real value. So if we've got the logarithm of x minus 2, that is going to be positive and real only if x is greater than 2. Likewise, the second term in this equation, we've got the logarithm of x plus 3. Now this is only going to be defined when values of x are greater than -3, because this quantity inside the brackets needs to be positive and real. And really what we're looking at is the intersection of those two sets. So on the one hand, I need values of x that are greater than 2. On the other hand, I also need values of x that are greater than -3. The values of x that satisfy both of those inequalities at the same time, or the intersection of those two sets, when x is greater than 2. So if I go down here and have a look at the solutions to my quadratic equation, -5 is not going to be one of the solutions to this equation. It certainly is a solution to the quadratic equation, but it's not a solution to this one. So, and this is particularly important in VCE exams. Examiners will give you full marks if and only when you explain the fact that you are disregarding one of the solutions that you found here. So I've finished off the problem by stating that x is equal to 4 only, since x must be a value that's greater than +2. So that's all we're looking at today. So just a quick review. We've seen how do we use our log laws to solve logarithmic equations, and in one case we've seen why it's important to consider whether or not the apparent solutions of an equation exist. It's actually just good problem solving practice to always ask, do my solutions seem reasonable? Do they make sense? Thanks very much.